Hi and welcome to video 9 of Newton's Laws set of videos, and this is part of our forces topic in Unit 4, Topic 2, Specialist Mathematics. And so we'll be looking at Newton's Law as a continuation on our work with acceleration in different forms of acceleration and simple harmonic motion. Let's have a quick look at the laws and summarize them. The laws as they stand were written quite a long time ago, obviously, but I'm going to try and bring out the actual equations and relationships that they themselves bring about. So law number 1 is that a body remains stationary or in uniform straight line motion unless acted on by an external force. So if you have something that is currently just sitting still, stationary, or perhaps it's moving but there's no force acting on it, it will continue to sit still, be stationary, or move at the same velocity. Nothing will change. There will be no acceleration applied because there's no force applied. Of course, in real life, there is other forces that we usually don't consider, such as wind resistance or just wind or drag or whatever, along with other things. So that's never often the case that there's no forces, but sometimes there's negligible forces. Law number 2, a body acted on by forces will have the rate of change of momentum is proportional to force. So we say that momentum, which is P, the rate of change of the momentum is proportional to force, and of course that means that we end up with, and we can follow this process here, we end up with force equals ma. That's where this goes. You've probably heard of force equals ma, maybe you've done it in physics. If you have, this is where it comes from, this idea. So we get that the rate of change of momentum is equal to or proportional to force, and d to t of momentum is proportional to force, which means it equals k times f, which means m d to t of v equals kf, which means ma equals kf, and we're lucky enough to have defined this whole situation, so we just set the units for force, newtons, such that it absorbs the idea of k, and so we just have force equals ma. So that's law number 2, and it brings about force equals ma. And law number 3, any force acted on by body A or by body B implies an equal opposite force of A on B. Any force, and law number 3, any force acting on body A by body B implies an equal and opposite force by A on B. So it's not written perfectly there, but basically if body B applies a force on body A, well, body A will apply a force back on B. Even if it doesn't seem like it, body B is now not moving forward the way it might have, or whatever the situation is, because body A is restricting that movement perhaps. So this is where we get the idea of normal reactive forces. Some work with connected particles, and also a little bit of the work with friction we're going to see soon. So they're Newton's laws, but we're really concerned with the math behind them. So let's have a look. First of all, here's our formula sheet. So it's nice to note on here our simple harmonic motion, our acceleration laws, but we are missing a couple. So force equals ma is not there. Momentum equals m times v is also not there. Which I've put a little sad face there, but to be honest, they're fairly simple functions, so hopefully they're right and we can deal with those. So let's have a look at a simple example. I've kind of written here, shall I assume that you know the simple stuff? Well, I'm not going to in this video, but I may do in class. We'll run through this example very quickly. And I'll say simple stuff. There's actually a collaboration of ideas in this one example, but they're all fairly simple ideas. So first, a mass of 16 kilograms is acted on by a force of 30 newtons and a force of 40 newtons, and these forces are perpendicular to each other. So we've got force and mass, which means we can get acceleration. Now, the object is initially stationary, so we're given an initial point for velocity. How fast is it going after 10 seconds? So we want the velocity after 10 seconds. We can work out the acceleration. If we integrate acceleration, we get velocity with a constant, but we know a data point for velocity, the initial data point where the velocity equals 0. So we can do all of this question. But we do have two forces acting on it, so we need an overall force, and we need to be considerate of whether we need to maintain magnitude and direction, and what's important in this question. So let's start with the force diagram. Here are my forces. I'll call this one the 40 newtons force, and this one is the 30 newtons force. And overall, my force acts up here, and you will note a little bit of Pythagoras will give us 50 newtons overall, but I'm not too worried about that because I'm going to set this as the I and J components, I and J like that, and that means that my resultant force, which I'm going to call R, is equal to 30I plus 40J. I'll zoom in on this now. 30I plus 40J is my resultant force, and of course that means that MA equals 30I plus 40J, which means that 16A equals 30I plus 40J, which is nice. 16 is not as nice a number as I could have chosen, I suppose, but A, which is a vector, so I should put that A there. M's a constant, it's a scalar mass, but my A is a vector, and so I get 30 over 16I plus 40 over 16J. And of course that means that velocity, I could put a little bit more working into this, but let's not. 30 over 16 is 15 over 8 Ti, plus 40 over 16 is 2.5, but I'll put it as 5 over 2 Tj. That's my velocity, but there is some constant because I've integrated acceleration to get to velocity there. But we do know this, at t equals 0, this object is stationary, so velocity equals 0, and therefore c equals 0. So that means that velocity is equal to 15 over 8t plus 5 over 2 tj, and at time equals 10 seconds, our velocity now is equal to 150 over 8I plus 50 over 2j. Which can be written as 18.75I, or 18 3/4, plus 25J. That's the velocity. The question kind of asks, how fast is it going? And fast is a word that's more associated with speed. There's no risk here. If I get this in an external exam, I could just quickly calculate the speed of that velocity. And the speed, of course, is just the magnitude of velocity. So 18.75 squared plus 25 squared, and that comes out as 31.25, and it's meters per second. So there's my speed, which is an indication of how fast I'm going. And 31.25 meters per second is pretty fast. Now, on this note, you'll notice here that I've used meters and seconds. And up here we've got work with kilograms. The 16 was in kilograms. So I just want to make the note here that we're using that MKS system again. And newtons, you remember, the standard Newton form is equal to kilograms meters per second squared. There's our M, and there's our A, so we call that. So kilogram meter per second squared, MKS, meters, kilograms, seconds are our go-to. So remember that, they're our go-to. Expect to see them pop up, and look for the other things. Look for kilometers, look for for grams, look for hours, and just make sure that you convert or that you work those into your question if you need to. But otherwise, if we've got a force-based thing with newtons, then we have to use MKS. So there we have it. Example 1 and video 9, all done and dusted. All the best.